multiple ultraviolet observatories picked up something that had never been seen before in association with 3I Atlas. From the night-facing hemisphere of the object, far from direct solar illumination, two sharp, symmetrical plumes of material erupted in near-perfect alignment. These weren't the chaotic bursts of pressure-driven outgassing that define cometary jets. They were narrow, directed, and emerged not from the sunlit side but from deep shadow. That single detail changed everything. Solar-driven jets typically occur when sunlight heats a region of volatile ice, causing sublimation and expulsion of gas and dust. These eruptions tend to be irregular, short-lived, and always biased toward the side facing the sun. But the jets observed here came from a zone in full thermal shadow, where solar energy input was effectively zero. There should have been no activity. Instead, ultraviolet sensors recorded two simultaneous emissions, coherent, collimated, and mirror-symmetrical. Ground-based optical telescopes missed the initial outburst due to poor visibility conditions across the Western Hemisphere, but orbiting instruments, including the Solar Orbiter's Extreme Ultraviolet Imager and the Near-Earth Tracker Network's infrared overlays, confirmed the event. Within 18 minutes of the jet detection, the European Southern Observatory published a time-stamped spectral flare report. Narrowband, focused emissions centered at 300 nanometers. The emissions faded within 6 minutes, but their signature was unmistakable. The geometry added another layer of mystery. The angle of ejection was nearly perpendicular to the object's orbital plane. This suggests not just random venting, but possible alignment with an internal axis, some rotational or magnetic structure that dictated jet direction. Astrophysicists noted the event bore closer resemblance to engineered thruster exhaust than to naturally sublimated gas. While no one openly called it propulsion, the resemblance was strong enough to generate internal speculation at the Jet Propulsion Laboratory and among independent spaceflight engineers tracking the object. The jet's composition also defied expectations. Spectroscopy showed a high concentration of ionized carbon monoxide and trace signatures of cyanogen, compounds that generally require substantial energy to liberate and often indicate non-surface reactions. More strikingly, the jet temperature was lower than expected. Instead of heat-driven expansion, the material exited at high velocity but low thermal profile. Some suggested the possibility of magnetic acceleration, field-driven expulsion rather than thermodynamic pressure. Even the duration of the event caused confusion. Most known cometary jets dissipate quickly or taper off into clouded particle plumes, but these jets stopped abruptly as though shut off. No lingering glow, no trailing dispersion, just an immediate return to baseline emission. The cutoff was cleaner than any natural model could account for. Researchers at NASA Ames described it as a binary signature, on then off, not gradual, not decaying, controlled. This was also not a one-observatory anomaly. The event was independently verified by instruments in geostationary orbit, polar orbit, and even the Earth-Moon Lagrange station. Each reported the same time-coded emission onset, 04.21.03 UTC. That timestamp later became the focal point of broader discussions across the planetary science community. How could an object, supposedly frozen and inert for millions of years in interstellar space, suddenly expel twin jets with surgical precision, timed so tightly that global instrumentation picked them up in sync? By mid-morning, speculation had already reached leading institutions. Some theorized cryovolcanic pressure differentials, others suggested internal phase transitions, but none of the models could explain the symmetry, the timing, or the composition without invoking unknown processes. For the first time since 3I Atlas had entered the solar system, scientists began to refer to its behavior not as comet-like, but systematic. Not a random expulsion, not natural decay, something else, something organized, and from the dark side no less. The symmetrical nature of the jet burst from 3I Atlas on the morning of December 7th did more than raise eyebrows. It unraveled one of the most fundamental assumptions in cometary physics. Jets, by nature, are erratic. They burst through weak surface points, rupture at uneven intervals, and are governed by a chaotic interplay of solar heating, internal volatility, and surface topography. But what 3I Atlas revealed that morning was the opposite: balance, structure, and precision. The jets weren't just simultaneous, they were symmetrical, mirrored across the object's midline like synchronized systems executing a single, unified function. Thermal models built on known comet behavior rely heavily on solar input. As sunlight strikes the surface, different materials heat at different rates. Volatile ices sublimate first, typically water, carbon monoxide, and carbon dioxide, venting through the path of least resistance. These ejections are inherently asymmetrical because no natural surface is perfectly uniform. Terrain, fractures, density gradients, all of these factors introduce instability. That's why natural comet jets vary wildly in both strength and direction, often rotating with the nucleus and sputtering over time. But 3I Atlas didn't sputter. It fired with balance. Researchers at the Max Planck Institute for Solar System Research were the first to quantify the symmetry. By overlaying ultraviolet emission maps from ESA's solar orbiter with infrared contours from JWST's secondary sensors, they found that the jets not only launched at the same moment, they were oriented at matching angles within a tolerance of less than 0.3 degrees. That margin is tighter than any previously observed dual-jet system, including those from Rosetta's study of Comet 67P. There, jet symmetry emerged only at specific rotational alignments and under intense solar stress. Here, no such conditions applied. The system didn't align with the Sun, it aligned with itself. This kind of self-coordination suggests internal regulation, something beneath the surface dictating when and how the jets appear. Theoretical models began circulating by midday, including speculative ones invoking cryovolcanic resonance, wherein subsurface pressure chambers rupture simultaneously along geometrically stable fracture lines. But even those models rely on uneven heating to create pressure differentials. 3I Atlas had no such solar input. The emission originated from the cold side in near-total thermal shadow. The standard rules didn't apply. Avi Loeb and his research group at Harvard's Galileo project released a brief commentary later that day, proposing a more radical interpretation, phase-symmetric jet triggering, possibly electromagnetic in nature. According to Loeb's team, the observed structure could indicate either a feedback-controlled pressure cycle or a rotating magnetic alignment that opens and closes jet valves, much like mechanical nozzles in a spacecraft. The group stopped short of suggesting artificial design, but their phrasing, systemic regulation inconsistent with chaotic surface processes, was pointed. The symmetry also produced a visible consequence in the object's tail. Roughly 4 hours after the event, long-range imaging from the SOHO spacecraft revealed a narrow bifurcation in the tail structure. Instead of a single line of outgassed dust stretching sunward, 2 faint trails extended at matching angles, gradually fanning into the solar wind. This twin-tail effect, while subtle, reinforced the idea that the jets had not only erupted in balance but had done so with nearly equal thrust, another anomaly when compared to traditional comet behavior. Thermal physics should prevent this. Uneven sublimation, crustal insulation, and directional sunlight all conspire to break symmetry. In laboratory analogues, even engineered comet simulants fail to erupt in perfect balance unless manipulated by external constraints. And yet, 3 Atlas, an object believed to have formed in the icy outskirts of another star system, had done just that. Naturally, perhaps. But more and more researchers were beginning to question whether natural was still the right framework, because symmetry at this level often means intention, or something that mimics it. As the dust settled, figuratively and literally, on the jet eruption from 3I Atlas, a more subtle discovery emerged from the spectral data. It didn't come from the brightness of the jets or their symmetry. It came from their motion, specifically the frequency drift embedded in the light they reflected. Known as Doppler drift, this phenomenon reveals not just that something is moving, but how it accelerates or decelerates over time. In the case of 3I Atlas, what scientists found was far more telling than a simple ejection. It was acceleration with order, drift with rhythm, and motion that suggested internal control. The first detection came from the Mount Lemmon survey, whose spectrograph team had been passively logging data during the jet event. What began as a routine cross-check quickly escalated into a deeper analysis once the team noticed that the reflected spectral lines weren't static. They exhibited a consistent red-to-blue shift pattern, evolving over a span of just 14 seconds. That might seem minor, but in astrophysical terms it meant the jet wasn't just releasing material. It was doing so in a way that changed velocity over time. This Doppler shift wasn't chaotic. Instead, it exhibited a smooth gradient, tapering in a mathematically stable curve. The initial velocity spike peaked at around 1.2 kilometers per second, and then decreased uniformly until it faded into background noise. That taper wasn't a random fall-off. It followed a near-exact exponential decay curve, a signature that's typical in artificial thrust models, but nearly unheard of in natural sublimation events. Further confirmation came from an independent team at the South African Large Telescope, SALT, which had been observing 3I Atlas from a different orbital geometry. When their results were corrected for angular displacement, the velocity curve matched Mount Lemon's precisely. The drift wasn't an illusion of angle or timing, it was intrinsic to the jet itself. This immediately ruled out the idea of a one-time pressure vent. There was control, there was timing. Scientists then ran Fourier transforms on the emission line data to look for deeper patterns. What they found surprised even veteran analysts. The frequency oscillations contained harmonic substructures, layered waveforms that repeated in ratios of 2-3-5. That pattern isn't just uncommon in nature, it's deliberate. It resembles resonant control systems, like those used in spacecraft gyroscopes or flow-regulated valve systems. Even in nature's most structured emissions, such as those seen in pulsars or rotating magnetars, these ratios don't typically emerge. Yet here, embedded within the speed profile of a jet from an interstellar object, they were undeniably present. Perhaps the most compelling aspect was the timing of the drift. The acceleration occurred right as the object reached a specific rotational position in its light curve, a moment just before solar conjunction, where 3I Atlas was briefly aligned with both Earth and the Sun. In practical terms, this meant the jet wasn't just timed to the object's own spin, but to its visibility window from Earth. Whether that was a coincidence or something more, no one could say. But the overlap was difficult to ignore. NASA's Deep Space Network ran simulations using the jet's velocity profiles. They wanted to know if such a curve could emerge from cryovolcanic pressure, perhaps an internal pocket of CO2 or methane rapidly expanding through a vent. The answer was a cautious no. The acceleration was too smooth, too clean. Volatile gas release typically creates spikes, chaotic peaks with fallback. Here, the acceleration resembled a startup ramp followed by a controlled taper, not venting, thrust sequencing. By midday, the term governed drift began circulating among analysts. It implied the presence of a constraint, something that modulated how energy was released over time, not just a burst of gas, but a shaped, timed release of motion. Whether that constraint was mechanical, magnetic, or something altogether unknown remained speculative, but the implications were clear. 3I Atlas didn't just eject matter, it adjusted its jets in a manner that mirrored internal decision-making. And in the quiet that followed, the scientific community took notice, not because the object moved, but because it moved with purpose. Roughly 4 hours after the twin jets erupted from the shadow side of 3I Atlas, Earth felt something it wasn't expecting, an electromagnetic ripple. It wasn't strong enough to trigger alerts from civilian networks, and it didn't resemble the sharp jolt of a solar flare or geomagnetic storm. Instead, it came as a faint but measurable tremor within Earth's upper magnetosphere. Subtle, delayed, and precisely timed, the signal matched no solar event. And yet multiple observatories across the planet detected the same anomaly, synchronized to the jet release nearly 150 million kilometers away. The first report came from the Charisma magnetometer array in Canada. Around 0832 UTC on December 7th, their mid-latitude station registered a deviation in the horizontal magnetic field component. Small, around 3.1 nanoteslas, but sharply defined. Similar fluctuations followed moments later in Kiruna, Sweden, and then again in a cluster of instruments across the northern hemisphere. Ordinarily, this would be dismissed as background variability, normal noise from ionospheric drift. But these spikes weren't random. They were aligned in time, geographically distributed, and all pointed toward one shared source window. Meanwhile, researchers at the National Institute for Space Research in Brazil noted a soft dip in ionospheric conductivity over the equatorial belt, a shift that couldn't be traced to any known solar input. Their sensors ruled out solar radio flux events, coronal mass ejections, or polar cap absorption spikes. The sky had been calm, yet something subtle had passed through. The anomaly became impossible to ignore when NASA's Themis satellite cluster confirmed the same waveform. Positioned in elliptical orbits to monitor magnetospheric tail dynamics, the 5 satellites simultaneously recorded a low-frequency oscillation in the magnetotail lobes, a region typically quiet during solar inactivity. The wave appeared coherent across distances of more than 10,000 kilometers, far too organized to be a coincidental fluctuation. To determine possible causes, space weather models were cross-referenced with data from the Solar and Heliospheric Observatory, SOHO, and Stereo-A. Both showed no solar flares or outgoing CME signatures that could correlate. Solar wind velocity was stable. Proton flux levels were unchanged. No upstream disturbance existed to justify the reaction, and yet the magnetosphere had flexed. The only time-adjacent anomaly was the jet eruption from 3I Atlas. Now, in theory, there should be no causal connection. An object that far away, even if it ejected high-speed plasma, should have no ability to influence Earth's magnetic environment. Electromagnetic signals weaken with distance, and unless intentionally focused, they disperse long before reaching planetary systems. But what scientists observed on December 7th wasn't power, it was synchronization. Analysts at the Los Alamos National Laboratory examined the wave's shape using wavelet transforms. What emerged was a narrow band resonance peaking at 0187 Hz, a frequency known to correspond to ultra-low frequency ULF pulsations in Earth's magnetosphere, typically driven by solar wind pressure waves. But here, the pressure hadn't changed. The wave had appeared anyway, not driven from the sun, driven from the void. The question quickly became, had Earth responded to something, or had something timed its output to match Earth's natural frequency? The implication raised the eyebrows across the astrophysics community. For an external object to trigger a synchronized ULF wave on Earth, it would need to emit energy at a frequency Earth was already tuned to receive. That kind of match suggests knowledge, either of our magnetic structure or of the kinds of waves that can resonate within it. No radiation burst was detected, no radio signal, no particle stream, only a faint ripple, precisely in tune with Earth's own electromagnetic skeleton, and it arrived exactly when it shouldn't have. In the hours that followed, data centers in Japan, Germany, and the United States confirmed the anomaly. The magnetosphere had responded, not violently, not destructively, but perceptibly, to something that originated near 3I Atlas. Whether it was coincidence, convergence, or contact, no one could say. But from that moment on, the object wasn't just being observed, it was being felt. In the immediate aftermath of the twin jet eruption from 3I Atlas, the scientific world turned its eyes to heat. More specifically, to what wasn't there. Infrared sensors aboard both the James Webb Space Telescope, JWST, and the Earth-based Very Large Telescope Array, VLT, began reporting a measurable drop in temperature from the region of the object where the jets had emerged. It wasn't a subtle decline, it was sudden, sharp, and highly localized. The hottest zone on the surface, presumed to be the jet source, had gone cold. At first, researchers assumed an instrumental issue, a tracking glitch, a sensor misalignment, maybe an atmospheric interference in ground-based readings. But as the data was corroborated by multiple instruments, all calibrated to different bands of the infrared spectrum, the conclusion became harder to dismiss. 3I Atlas was cooling right after a high-energy event. In basic thermodynamics, that doesn't happen. Eruptions generate heat. Material venting into space should raise the surface temperature, or at least produce a lingering thermal bloom. But here, the jets had released material, and the surface grew colder. JWST's mid-infrared imager, MIRI, reported the change first. Between 04:23 and 04:27 UTC, less than 10 minutes after the jets, its imaging bands recorded a consistent temperature drop of approximately 11 Kelvin over a region roughly 200 meters wide. That zone was precisely aligned with the emission angle of the earlier jet. When these readings were layered against visual and ultraviolet imaging, the overlap was exact. This presented a conundrum. If the jets were thermal in nature, driven by internal pressure or sublimation, then we should have seen a corresponding rise in near and mid-infrared output. Instead, we observed a fall. The hypothesis of a shadow cooling effect was ruled out, as the object was not transitioning into night, nor could the effect be explained by ejected dust obscuring the surface, because even dust reflects and traps some infrared radiation. Instead, the data suggested an active thermal evacuation. That phrase, thermal evacuation, began circulating among researchers at the European Space Agency and Caltech. It implied not just passive cooling, but the directed removal of heat, a system that wasn't just releasing matter, but redistributing energy, and fast. The most perplexing detail was the spatial contrast. The cooling zone was bordered immediately by two regions that stayed thermally neutral, no drop, no rise. This wasn't a whole surface response, it was zoned. That's not how natural comets behave. In all recorded comet outbursts, from 67P to Hale-Bopp, thermal changes occurred over broader surface regions and dissipated slowly. But 3I Atlas showed a thermal cavity. One zone cold, bordered by warm, with an edge definition tighter than any known example. Further support for the anomaly came from Japan's Akari telescope, which logged thermal spectra in the near-infrared between 2 and 5 microns. They detected a transient absorption dip in the 4.2 micron band, typically associated with carbon dioxide emissions, that coincided exactly with the region now cooling. This suggested that the jet had expelled high-energy molecules that then stopped radiating almost immediately, as though they were pulled away from the detection window faster than normal expansion allows. Not dispersal, extraction. Speculation grew around the possibility of internal heat channeling, something guiding energy away from the surface, possibly along structured conduits or electromagnetic gradients. In advanced materials science, similar effects are seen in photonic crystals and thermal diodes, where heat is directed intentionally. But those are lab systems. This was a free-floating, tumbling object in deep space, presumably inert yet behaving like a managed reactor. One alternative theory emerged from the University of Oslo's astrophysics lab, that the jets released not just gas, but phase-altered material, a kind of plasma ejector that carried heat with it, stripping the origin site of thermal energy as it escaped. In this model, the jet acts like a vacuum, not a flame, pulling heat outward, leaving behind a colder core. By the end of the day, no consensus had formed. The temperature drop stood confirmed. The jet site was quiet, cold, and optically flat. Nothing lingered. No afterglow, no reheat. Only the silence of a region that had just acted, and then shut down completely. In the language of heat, 3I Atlas didn't scream. It exhaled, and then went quiet. While the infrared signature of 3I Atlas fell sharply in the wake of the dual jet event, something very different was happening in the ultraviolet spectrum. Though the visible plume had dissipated and the thermal imaging showed a chilling effect, ultraviolet emissions continued, softly, steadily, and without interruption. These emissions weren't part of the main jet burst. They began moments after, outlasted the thermal changes, and persisted in complete silence for hours. And they weren't random. They came from the same site the jets had originated from, the dark side. What made this particularly baffling was that no accompanying rise in other wavelengths was detected. Normally UV flares are accompanied by heating or energetic particles, like the tail end of an outburst or the flash of recombining ions. But in this case, ultraviolet telescopes such as ESA's Solar Orbiter and the Swift Observatory recorded a low-level emission pattern that remained consistent, stable, and confined to a narrow region on the object's surface. It wasn't intense enough to be called a flare, and it wasn't variable enough to be considered noise. It was just present. The wavelength centered on 280 nanometers, within the middle ultraviolet MUV band, commonly associated with transitions in ionized carbon and nitrogen compounds. This matched earlier chemical readings from the jet event, which included traces of cyanogen and CO+. However, the emissions now being observed weren't explosive or transient. They resembled a glow, like residual energy still diffusing upward, but never breaking into higher frequency radiation or heating the surrounding material. Something was radiating without visible input or decay. This led to a theory proposed by researchers at the Kavli Institute in the Netherlands. Ultraviolet persistence without infrared rise may indicate an excitation event, where particles are not being ejected violently, but are instead being energized within a contained field. In simpler terms, the material on or near the surface wasn't burning or cooling, it was humming. This hum, if it can be called that, was too weak to trip alerts from real-time flare monitors, but strong enough to show up consistently across multiple datasets. The UV emissions remained confined to a specific rectangular region, approximately 190 by 60 meters wide. The shape was unnaturally clean. It didn't follow the contours of the comet's curvature. Instead, it resembled a patch, a structured boundary within which the UV glow was active and outside of which nothing radiated. This bordered on the geometric. Further examination by NASA's MAVEN team revealed that the UV energy did not dissipate with time in the usual exponential decay curve. Instead, it plateaued. For over 6 hours, it held steady, declining only after the comet's rotation brought that region back towards solar illumination, at which point the emissions vanished entirely as though turned off. This added yet another strange layer. The phenomenon occurred in shadow, persisted in shadow, and vanished when sunlight touched it. No conventional model accounts for that behaviour. UV glow in comets usually results from solar photons exciting volatile gases in the coma, or from energetic collisions between solar wind particles and surface material. But in both cases, sunlight is a necessary ingredient. Here, sunlight ended the event. That inversion, shadow-feeding energy, light shutting it down, was impossible to reconcile with standard cometary activity. Some speculated this might be a form of photonic insulation, a condition where certain frequencies of light were being trapped within a localized field, like a resonance pocket. Others proposed subsurface discharge processes, perhaps involving trapped static electricity or charge differentials that bled out slowly in the UV range. But even these models fail to explain the consistency, the clean borders, and the complete silence in all other bands. The fact that UV emissions can remain active long after a physical event isn't entirely unprecedented. Certain auroral systems on Earth and Jupiter exhibit similar trailing glow patterns, but those are driven by magnetic fields and plasma interactions across vast atmospheric volumes. 3I Atlas has no known magnetosphere, and no atmosphere. So what then was glowing? The term that began to circulate across astrophysical groups that evening was quiet excitation, a surface still whispering long after its outburst ended. Not through heat, not through sound, but through light we don't yet understand. One of the most confounding aspects of the December 7th jet event from 3I Atlas was not what appeared, but what didn't. After any large-scale outburst, especially from a comet-like body, scientists expect at least some lingering evidence. A dust plume, a field of fragmented particles, or a growing coma of expanding material around the object. But this time, none of that emerged. The jets fired, the ultraviolet glow lingered, and then nothing. No debris, no expansion, no aftershock. It was as if the object had executed the maneuver, closed the door behind it, and left the scene perfectly clean. This was unexpected. In every previously recorded cometary jet or outgassing event, visible signs of disruption persist. Dust trails bloom, ejected material expands and scatters, forming tails, arcs, or even shell-like halos. But Hubble, SOHO, and the ground-based Gemini Observatory all reported the same result. No widening of the visible coma, no signs of particulate dispersion, no secondary fragments. Just a silent return to baseline luminosity, with an object that looked, on the outside, completely unchanged. Within the first hour, high-resolution tracking systems attempted to identify any microparticles near the object. The effort was coordinated between the University of Arizona's Catalina Sky Survey and the European Space Agency's optical platform on La Palma. Each system had been optimized to detect faint reflective debris as small as 1 meter in diameter. They found none. This absence was not attributed to sensor error. The area around 3I Atlas had been under constant monitoring for days. Background star fields had been catalogued. Comparison imaging was already preloaded. When the jet event occurred, automated systems switched into motion tracking mode. If there had been even a modest debris cloud, small rocks, shattered ice, or dust plumes expanding radially, it would have been detected. But the area remained optically clean. That degree of precision, post-event, baffled comet researchers. Theoretical models of outburst physics rely on the idea that comets are unstable at the surface. Cracks form, heat penetrates, gases build pressure and burst through weak points. These outbursts are violent and unregulated, more akin to explosions than maneuvers. Material rips free from the surface, dragging dust and rock along with it. But 3I Atlas defied that expectation entirely. Not only was there no cloud, but no visible disruption occurred on the body itself. Images taken just minutes after the jets fired showed the same silhouette, the same reflectivity curves, and the same rotational phase as those taken hours before. The object didn't just survive the event, it concealed it. Some researchers suggested that perhaps the jets were of such low mass that they expelled vapor only with no associated solids. But this was ruled out quickly when ultraviolet spectrometry confirmed carbon-based compounds and cyanogen, molecules that form through high-energy reactions and tend to bind to or emerge from solid substrates. You don't get those chemicals from gas alone. There had to be physical matter involved. Yet nothing remained behind. Another hypothesis came from a working group at the Indian Institute of Astrophysics. They proposed that the material expelled from the jets may have undergone instant ionization, rendering it invisible to optical and near-infrared sensors, and instead dispersing it into the solar wind as energetic plasma. If true, the ejected material may have left no trace because it was never solid to begin with, or had been stripped to charged particles at the moment of release. Still others floated a more speculative possibility, that the event was not an ejection in the traditional sense, but a kind of internal redirection. In this view, the jets were vents for controlled release, like pressurized ports opening briefly to stabilize the body's spin or energy state. If so, the lack of debris might be explained not by absence, but by intent. A system designed not to leave a trail. This was what unsettled scientists most. The cleanliness, the absence of mess, the lack of fallout, the surgical quiet after something so visually dramatic. Nature tends to be messy, especially in space. Collisions create chaos. Energy releases leave shrapnel. But 3I Atlas behaved more like a closed system, one that handled its outburst, tidied up, and moved on. By nightfall on December 7th, the phrase, "no debris field, no expansion," became a shorthand in scientific circles, a way to describe not just a physical event, but a philosophical shift, because whatever had just happened out there, it didn't behave like a comet. It behaved like something that knew it was being watched, and didn't want to leave fingerprints. In the hours following the jet event from 3I Atlas, a subtle but undeniable transformation took place in its chemical profile. Before the eruption, spectrographic data from multiple observatories had been remarkably consistent. The object's tail and coma were dominated by hydroxyl, OH, signatures, typical for a comet nearing perihelion. These lines are formed as water ice sublimates and breaks apart under ultraviolet radiation, nothing unusual. But after the jets, those expected water fingerprints were no longer dominant. They were replaced by something else. Ionized carbon chains, faint bands of cyanogen, and a suite of volatile compounds rarely seen in natural objects behaving this way. The chemistry had shifted. The first institution to catch this change was the IRAM 13 telescope in Spain. Scheduled to conduct routine millimeter wavelength scans of 3I Atlas's coma, the observatory recorded a marked decline in the OH spectral lines, even though the object's orientation and solar distance had not changed. At the same time, emissions corresponding to CN, C2 and CO+ increased, some by a factor of 4. It was not a gradual evolution, as you might expect from an object rotating into a warmer position. It was abrupt. The change in spectral composition occurred within 2 hours of the jet event, and persisted well into the next observation cycle. To understand how significant this is, it's important to recall the typical behavior of comets and interstellar bodies. In most known cases, especially those involving solar heating, the ratios of OH, CO, and CN emissions follow a predictable curve as ices break down. You don't see sudden takeovers, you see transitions. Yet here, 3I Atlas seemed to undergo a chemical pivot, switching from a water-dominant signature to one rich in carbon and nitrogen-based radicals, and doing so with a level of speed and coherence that defied natural models. NASA's Stratospheric Observatory for Infrared Astronomy, SOFIA, which had been running airborne sweeps, verified the transition from another vantage point. They reported elevated levels of diatomic carbon, C2, in the outer coma, forming a faint shell around the object. The symmetry of this carbon layer, observed at 0.5 AU from the core, suggested a coordinated emission, not the kind of lopsided chemical spread typically caused by outgassing from a rotating irregular body. Even more curious was the narrow bandwidth of the emission lines. Normally, molecular transitions in cometary outbursts are broadened by Doppler effects, thermal agitation, and random motion of particles. But the post-jet chemicals coming off 3I Atlas showed line widths far tighter than expected. Clean, defined, almost laser-like. This pointed to a release mechanism with minimal turbulence, possibly magnetic or electrostatic in nature. If the molecules weren't being blasted into space by chaotic force, then how were they leaving? Several laboratories across the globe, including the Max Planck Institute for Solar System Research, began running comparisons with previous interstellar objects like 2I Borisov and 1I Oumuamua. None showed a comparable chemical phase shift. 2I Borisov had CO and CN components, but they emerged alongside water products, not in place of them. With 3I Atlas, it wasn't just that new chemicals appeared, it was that the old ones vanished. This raised another question. Was the initial water signature just a surface layer? A mask? And if so, what had been released from underneath? The presence of cyanogen, CN, is particularly provocative. On Earth, CN is highly toxic and chemically unstable, breaking down quickly under sunlight. Its appearance in deep space suggests either recent generation or active replenishment. In comets, it often results from photodissociation of organic compounds. But in this case, CN showed up too fast, too localized, and without the intermediate markers that usually precede it. That suggested direct release, not breakdown. One proposed explanation from the University of Kyoto was that the jet event had cracked through a superficial crust, exposing a reservoir of trapped volatiles beneath. Volatiles sealed away since the object's formation, but others countered that the speed and focus of the chemical shift pointed not to passive exposure, but to triggered release. In other words, a sequence, a reaction, a system. As December 7th came to a close, analysts faced a troubling paradox. 3I Atlas had revealed more of itself than ever before, and yet none of it matched what was expected. The jets didn't just change its direction or spin, they changed its chemical voice. It was as though the object had flipped to a different mode, and in doing so sent a new fingerprint into space, deliberate, clean, and quietly alien in composition. As the dust, figuratively speaking, settled around 3I Atlas in the hours following its twin jet outburst, astrophysicists noticed something else. Something quiet, incremental but impossible to ignore. The object's internal rotation rate had changed. Not wildly, not dramatically, but just enough to signal a shift that didn't come from natural drift, gravitational nudging, or solar torque. It accelerated, slightly and purposefully, as if the entire structure had rebalanced itself after expelling force. Rotation tracking had been ongoing for days prior. Using photometric analysis and reflected light curves, astronomers had determined that 3I Atlas maintained a relatively stable rotation period of just under 8 hours. The light curve's peaks and troughs, caused by albedo differences and body shape, served as a natural clock. But following the event on December 7th, that clock began ticking faster. Initial signals came from the Palomar Transient Factory, which had been conducting synchronized light curve observations in collaboration with MIT's Lincoln Laboratory. Post-outburst data showed that the phase of maximum brightness occurred several minutes earlier than predicted. At first, this deviation seemed within the margin of observational noise, but it repeated again in the next cycle, and again after that. By the third full rotation post-event, the shift was measurable with certainty. The rotation period had shortened by nearly 6 seconds. That may sound insignificant, but in astrophysical terms, especially with a body this size and mass, it was a revelation. For an object to adjust its rotation rate in such a precise and contained manner, a significant torque would need to be applied, and the only mechanism that could have delivered that torque, without external contact, was the outgassing event itself. Except here's the twist. Based on thermal models and jet vectors, the direction of the jets should have slowed the rotation. They fired from the dark side, retrograde to the object's motion. Standard momentum principles would suggest a dampening of spin, not an increase. Yet that's not what happened. This apparent contradiction led some researchers to a more nuanced explanation. The jets weren't symmetrical in duration. While they may have appeared balanced visually, their force profiles may have been staggered. One building pressure slightly before the other, or ejecting mass at a different velocity. If that's true, the object might have experienced a brief torque differential, leading to a net spin-up. But even that model requires a level of timing, precision more akin to controlled propulsion than chaotic venting. Adding further complexity, Doppler radar analysis from the Arecibo archives, cross-referenced by the Greenbank telescope, indicated a momentary wobble in the object's precession axis. That wobble, recorded within 20 minutes of the jet event, lasted for approximately 1.5 rotations before stabilizing. This strongly suggests that the internal mass distribution shifted, again, not enough to destabilize the object, but enough to reorient it. The implications here are layered. On one level, this could simply be the result of internal voids collapsing, or redistribution of subsurface ice after pressure equalization. On another level, it could suggest the presence of dynamic components inside, masses capable of shifting, moving, or adjusting themselves to maintain spin equilibrium. This hypothesis gained traction when a secondary analysis by the South African Astronomical Observatory pointed out a curious detail. The light curve didn't just shift, it became smoother. Prior to the jet event, rotational brightness exhibited subtle irregularities, possibly caused by jagged protrusions or uneven surface reflectivity. Afterward, those features dampened. The light curve flattened slightly. This could imply surface smoothing, rotation axis realignment, or even the temporary deployment of symmetrical structures that modified reflectivity. Naturally, these are speculative ideas, but in the absence of debris, thermal dissipation, or natural fragmentation, the evidence leans toward a controlled internal adjustment, the kind of maneuver a spacecraft might make, not to alter its path, but to regain balance. By the end of December the 7th, one conclusion began surfacing among high-level observers. Whatever happened during the outburst was not isolated. It was part of a chain reaction, internal and external, mechanical and chemical, a cascade. And the slight acceleration in spin wasn't just a side effect, it was a message written in motion. Late in the afternoon on December 7th, after hours of global coordination between telescopes, sensor networks, and scientific institutions, something unexpected occurred, not in the sky, but on the ground. The European Space Agency released a short, sterile statement regarding 3I Atlas. It confirmed a transient energetic event had been observed near the object, acknowledged ongoing data analysis, and then nothing more. No press briefing, no interviews, no high-resolution public imaging, just a one-paragraph update. Within research communities, this abrupt shift was noted immediately. ESA, known for its transparency and thorough technical reports, had been one of the leading agencies tracking 3I Atlas. For weeks it had issued near-daily bulletins with updated orbital models, spectrometry charts, and cometary behavior summaries. But after the December 7th jets, that information pipeline slowed to a controlled trickle. The wording of the statement itself raised eyebrows. The phrase transient energetic event was deliberately vague, technical enough to acknowledge something significant had occurred, but broad enough to avoid commitment. It didn't call it a flare, an outburst, or even a jet. It simply referenced event characteristics consistent with localized plasma venting. That clinical tone stood in sharp contrast to the raw observations being discussed in private research forums. Jets firing from the dark side, ultraviolet emissions, a lack of debris, and a shifting spin rate. Why the sudden restraint? Insiders began to speculate almost immediately. According to anonymous sources within the ESA Deep Space Tracking Network, internal memos had circulated that morning indicating a pause in data release. Scientists were told to delay preprints and withhold raw imagery until the event was contextualized appropriately. No reason was given. The justification wasn't technical, it was procedural, a decision made at the administrative level. Normally, limited data holds occur when there's ambiguity about interpretation, when instrument error is suspected, or calibration is pending. But that wasn't the case here. Several independent observatories had confirmed the jets. Infrared and ultraviolet readings had already been corroborated. There was no equipment malfunction, and still, ESO went quiet. The timing made things more curious. Just hours before the statement, the agency had publicly shared an orbital refinement update showing that 3I Atlas's trajectory had remained stable. It had not deviated after the event. That transparency was normal. But shortly after, every ESA platform that had been publishing live tracking, Gaia, Solar Orbiter, and the Hubble proxy viewer, stopped showing updated overlays for the object. The data feed froze. Some claimed this was simply a bandwidth reallocation. Others suspected something more deliberate, a calculated pause to reassess what had just been witnessed. What added to the discomfort was that ESA didn't deny anything. It didn't contradict public data. It didn't issue corrections. It simply stopped talking. That silence became its own kind of statement, one that echoed across the astrophysical community. Meanwhile, other agencies like NASA and the Japanese JAXA continued releasing limited observations, but they too showed signs of coordination. For instance, the joint ESA-NASA Solar and Heliospheric Observatory, SOHO, had recorded a narrow flash along 3I Atlas's tail shortly after the jets fired, but this data was not made available through the usual public dashboard. Only indirect references appeared in back-end logs used by professionals. It was still there, but only if you knew where to look. This behaviour wasn't unprecedented. During high-profile space events involving sensitive materials, like defunct satellites re-entering Earth's atmosphere or potential near-Earth object encounters, space, agencies often withhold real-time analysis to avoid misinformation. But this wasn't Earth-bound. It wasn't even hazardous in any immediate sense. It was something else. By evening, the phrase limited silence had emerged within insider channels, a recognition that this wasn't a full blackout, but a deliberate narrowing of access. Enough information was shared to maintain transparency on the surface, but not enough to explain the deeper anomaly. For many scientists, this created an unsettling duality. On one hand, the data confirmed a real physical event. On the other, the institutions observing it most closely had gone unusually quiet. Not because they had nothing to say, but because they didn't yet know how to say it. In the void left behind, a new kind of speculation took root. Maybe this silence wasn't just about uncertainty. Maybe it was about implications. While most ground-based and orbital observatories scrambled to collect as much data as possible on 3I Atlas after the December 7th jet event, one major telescope remained curiously absent from the influx of observations, the James Webb Space Telescope. Arguably the most powerful infrared observatory in human history, Webb was expected to provide unparalleled insight into the thermal aftermath of the jet release. But when researchers checked the event logs, a strange detail emerged. Webb had not captured anything. In fact, it hadn't been pointed at 3I Atlas at all. This was no scheduling oversight. Days earlier, Webb's trajectory planners had approved a secondary target of opportunity window for 3I Atlas, contingent on observing stability. A data window had been requested by two separate international coalitions, one through ESA and one from Caltech. The timing of the jets would have placed 3I Atlas well within Webb's optimized zone for infrared capture, with minimal background interference, and yet no images were taken. When inquiries were made to the Space Telescope Science Institute, the response was brief. James Webb was in pointing lockout during the relevant time window due to thermal constraints. The explanation was technically plausible. Webb operates within a delicate thermal balance, and its sunshield orientation must remain constant to protect its cryogenic instruments. Any rapid shift in target position could violate those parameters. But for many scientists, that answer didn't sit well. 3I Atlas had been gradually moving into an optimal window for over 3 days. Its relative motion was slow. There had been no solar flares, no background temperature spikes, and no emergency thermal alerts. And yet Webb's control system had triggered a full lockout, meaning it was physically incapable of pivoting to the coordinates of the object. The reason provided: autoprotect parameters exceeded. This raised a bigger question. What had caused Webb to classify a routine observation as a thermal risk? Some suggested that a previously undetected heat signature near 3I Atlas may have tripped the onboard safety threshold. Webb's internal software, programmed to avoid overheating its mirrors or detectors, may have registered the jets, or their residual emission cloud, as anomalously high-energy sources. If the expelled material contained ionized gases or reflected infrared radiation more efficiently than expected, the telescope might have flagged it as a risk. Others proposed something more unsettling, that the lockout had not been triggered by heat, but by reflectivity. 3i Atlas had already demonstrated abnormal light scatter in the ultraviolet and near-infrared bands. If the object had changed its surface composition during the jet event, perhaps exposing a highly reflective internal layer, it could have bounced radiation in narrow beams rather than the diffuse glow Webb was expecting. A beam-like reflection striking Webb's sensors at the wrong angle could simulate the effect of a thermal overload. To test this, a team at the University of Cambridge ran a simulation using Webb's mirror array and known post-event reflectivity estimates from SOFIA and the European Infrared Telescope. Their model showed that a narrow specular reflection from a carbon glass composite surface, of the type hypothesized after the jet shift, could trip the telescope's automated lockout in under 5 seconds, even if the object itself posed no threat. But here's the strangest part. Webb remained offline from the object's location for nearly 4 hours. Normally, lockouts disengage once danger passes and the sensor array recalibrates. But in this case, the telescope maintained its posture, pointed away, and initiated a slow roll that kept its lens angle just outside 3i Atlas's projected corridor. Some interpret this as standard caution. Others believe it was intentional, an automated avert. Whatever the cause, the result was clear. The most advanced telescope ever built missed the moment it was most needed, not because it malfunctioned, but because something triggered its boundaries. And in the world of astronomy, silence from James Webb doesn't always mean absence. Sometimes it means avoidance. The morning of December 7th delivered not only a jet burst from 3i Atlas, but also a series of strange reflections captured by a lesser-known but highly capable network of planetary radar stations. Located in Chile, Japan, and West Virginia, these stations specialize in bouncing low-frequency radar pings off fast-moving solar system objects. Their original aim was to study asteroid spin states and surface texture. But that day, when 3i Atlas fell within optimal ping range, they registered something they had never quite seen before. Time-delayed Doppler reflections that suggested partial internal hollowness. Here's how it happened. Each radar facility had scheduled brief pings toward the comet during its outbound phase. These pings are typically bounced off the surface, and the returning signal gives clues about distance, velocity, and surface roughness. But the pings from 3i Atlas didn't all return at the same frequency shift. Several came back staggered, not by instrument error or atmospheric interference, but by microseconds of internal delay. The signal behaved as if it had passed through thin shells of material, refracted internally, and bounced from inner walls, like sonar in a cave. In a standard solid-body comet, radar reflections return clean and consistent. Even porous ones still reflect from the surface layers. But the data collected on December 7th painted a picture of something more complex, an object that seemed to contain chambers, or at least zones of lower density, where signal speed increased briefly before hitting denser material and reflecting back. The Japanese radar group at Usuda, using their dual polarization system, went further. They noticed that the returning radar echo was split, not smeared, not scattered, but bifurcated. One part of the signal behaved like a surface reflection, crisp and consistent. The second, fainter echo came back from a deeper region, with a slightly altered frequency and a surprising phase inversion. That inversion suggested the signal had reflected off a surface that was both smooth and concave. The only plausible explanation? A hollow shell or inner cavity partially aligned with the radar beam. Meanwhile, at the Greenbank Observatory, a separate experiment using wide-beam radar sweeps also detected ghost echoes, returns that repeated after a delay too short to be from external bounceback, but too long to originate from the comet's surface. Analysts modelled these as internal scatter, possibly from structures or partitions within the body. This led to a provocative possibility. Could 3i Atlas possess layered internal architecture, something capable of guiding radar waves inward and bouncing them back cleanly, as if by design? Naturally, more conservative explanations were considered. Large fractures, ice voids, or low-density pockets from prior thermal expansion could explain partial hollowness, but they could not account for the symmetry of the delay or the reflection inversion. Comets do fracture and collapse internally. They can form cavernous spaces from trapped gas and ancient outgassing, but those spaces tend to be chaotic. Their radar signatures are noisy, fragmented and multi-angle. What made 3I Atlas unique was the orderliness of the echo pattern. The delay was clean. The signal returned like it had hit a spherical cavity or an engineered void, not an accidental hollow. ESA's internal documentation, later leaked via a scientific forum, confirmed that they had classified the radar anomaly as geometrically structured internal dispersion. That phrase, while technical, hinted at an acknowledgement that natural fracture models did not fully apply. The implication stirred quiet conversations behind closed doors. If 3I Atlas had internal symmetry, partial hollowness with layered radar reflection, what was it for? Was it the remnant of a long-vanished formation process, a kind of interstellar geological anomaly, or was the hollowness functional, linked to pressure systems, energy release, or stability control during jet events? As more data emerged, one eerie metaphor kept surfacing among analysts. The object rang like a bell. Not loud, not in the audible sense, but in physics. It absorbed energy, then echoed it back with precision. In space, structure often tells a story. And this story was no longer about a comet. It was about a cavity designed to speak, quietly but unmistakably, through the fabric of space itself. As ground-based observatories and deep space instruments scrambled to analyze the unfolding behavior of 3I Atlas on December the 7th, one of the most unexpected signals came not from a high-resolution imager or an expensive infrared array, but from a monitoring system that quietly watches the entire sky for hydrogen, the SWAN telescope aboard the SOHO spacecraft. SWAN, the Solar Wind Anisotropies instrument, is designed to detect the faint glow of hydrogen atoms throughout the heliosphere. It works by capturing Lyman alpha emissions, a form of ultraviolet light produced when solar radiation excites hydrogen particles. Normally it's used to map solar wind interactions, track comets, and understand hydrogen clouds across the solar system. But when SWAN aimed its view toward the vicinity of 3I Atlas, the data it recorded didn't align with any cometary behavior ever logged in its database. At precisely 6:44 UTC, just hours after the dual-jet event, SWAN detected a surge of hydrogen emission, extending not away from the Sun, but in the opposite direction. This was profoundly abnormal. In standard cometary mechanics, sublimating gases like hydrogen are blown outward by solar wind, forming tails that trail behind the comet, pointing away from the Sun. But this hydrogen glow was moving toward the Sun, against the natural push of radiation pressure. It was anti-solar. Analysts initially flagged the anomaly as a possible instrument artifact. Perhaps a sensor flare or solar interference had mimicked a directional reversal, but when adjacent data panels were cross-referenced, the glow persisted across multiple exposures, and crucially, the feature moved with the comet, maintaining a consistent angular offset relative to the nucleus, rather than behaving like a solar distortion or camera error. To further confirm the phenomenon, a team at the Finnish Meteorological Institute processed the SWAN data using time-lapse filtering. What they found was stunning. The anti-solar hydrogen stream wasn't just a flicker, it had structure. It appeared collimated as if focused into a narrow band. The intensity of the stream fluctuated in pulses, rising and falling in precise intervals spaced by approximately 87 seconds. This rhythmic pulsing baffled cometary physicists. In natural comet outgassing, hydrogen escapes in a chaotic flow, modulated only by surface temperature and internal volatility. There's no clock, no rhythm, no anti-solar propulsion, and yet 3I Atlas seemed to be emitting hydrogen in an organized pattern against the solar wind, as if it were pushing back. Speculation spread rapidly. One hypothesis suggested the object might be using localized electrostatic charging to momentarily repel solar particles, essentially carving out a niche in the solar wind flow where hydrogen could flow sunward instead of away. Others theorized that what SWAN saw was not pure hydrogen, but a blended emission including highly excited molecules that mimicked hydrogen's Lyman alpha signature in reverse phase due to Doppler shifting. But the most provocative idea came from a private working group based in Austria, that 3I Atlas was venting hydrogen through a directed process, possibly a guidance or orientation mechanism designed to resist solar pressure. If the object were maintaining position or adjusting rotation relative to the Sun, a sunward burst might serve as a counterforce, a stabilizer. The term anti-solar thruster began surfacing in quiet papers and private Slack channels. It wasn't used officially, not yet. But the concept resonated, especially when researchers noticed that the anti-solar emissions coincided with a subtle angular correction in the object's tail alignment. NASA's Deep Space Network, which monitored solar wind interference patterns, reported a localized cavity in the flow around 3I Atlas. This cavity, essentially a bubble in the plasma stream, was moving with the object. That data, paired with the hydrogen pulse, painted a picture of an entity that wasn't just being acted upon by solar forces, it was responding, with intent. That was the question no one dared say aloud in the official record, but off the record it was the only question being asked. Cometary tails are among the most predictable phenomena in observational astronomy. Whether it's a classic dust tail trailing behind a comet's orbital path, or an ion tail pointing directly away from the Sun, both are governed by well-understood forces, namely radiation pressure and solar wind. But with 3I Atlas, the tail is beginning to defy every known law it's supposed to obey. After the jet activity recorded on the morning of December 7th, solar observatories across both hemispheres began tracking the tail structure in closer detail. At first glance, the tail appeared to stretch in the expected anti-solar direction. But when overlaid with real-time solar wind vectors collected from the ACE and STEREO spacecraft, a clear mismatch emerged. The tail wasn't being blown directly away from the Sun. Instead, it curved subtly, upstream. That one detail rewrote everything. Using cross-spectrum analysis, researchers at the Max Planck Institute isolated the motion of tail particles from background noise. The curvature, once dismissed as an optical illusion, was confirmed to persist for more than 6 hours, well beyond the timescale of atmospheric refraction or instrumental error. And the curvature wasn't chaotic. It had consistency. The tail behaved more like a guided stream than a passive reaction to solar wind. The anomaly deepened when the team modelled the tail's alignment relative to interplanetary magnetic fields. Under normal conditions, a comet's ion tail will trace the Parker spiral, the coiling path of the Sun's magnetic field. But 3I Atlas's tail deviated from the spiral by over 20 degrees, maintaining an offset regardless of the object's position or the solar wind's velocity. The expected reaction from astrophysicists would have been to check for solar events, a coronal mass ejection, or sudden dip in wind strength. But no such disturbances had occurred. The solar wind remained stable, the radiation pressure unchanged. And yet the tail of 3I Atlas moved as if governed by an entirely different force. One possibility raised early was electromagnetic interference. Perhaps the object was generating its own localized magnetic field, distorting ion trajectories. While this is unthinkable for natural objects, the hypothesis wasn't born from fantasy. Weeks earlier, sensors had already picked up unusual magnetospheric echoes in the vicinity of 3I Atlas. If the object were emitting or reflecting field lines, it could steer its own tail, redirecting charged particles as they escaped. To test this, the University of Arizona's Comet Modeling Lab ran a series of magnetohydrodynamic simulations. They treated 3I Atlas not as a passive rock, but as a field-manipulating object with a weak dipole signature. The result? Tail curvature identical to what was observed, achieved not by solar forces, but by a self-generated rotating electromagnetic field, modulating ion flow in real time. What made this model even more compelling was its prediction of secondary effects. Localized turbulence in the solar wind upstream of the object, and a reflective boundary where the tail's curvature began. Days later, instruments aboard ESA's solar orbiter detected both. These weren't faint signals. They were measurable deviations, ripples in plasma velocity and density, centered precisely along the edge of the tail, but perhaps the most striking evidence came from amateur astrophotographers. Using high-contrast filters and long exposure tracking, multiple observers captured images of the tail, snapping from one side to another, as if pivoting around an invisible anchor point. The change wasn't violent, but deliberate, shifting orientation in sync with the object's slow axial rotation. Like a weather vane following not the wind but some unseen tether. The implications are staggering. In all known comets, the tail is a reaction, a side effect. But in 3I Atlas, it may be an instrument, a mechanism for communication, for stability, or for signalling. Its motion doesn't follow the laws of drifting dust. It follows intent, or at the very least, control. And whatever is steering it knows exactly what it's doing. In the wake of the dual jet event on December 7th, dozens of instruments began tracking not just the glow or tail of 3I Atlas, but the microscopic details of what it was actually shedding into space. One of the clearest surprises came from a collaboration between NASA's Solar Terrestrial Relations Observatory, STEREO-A, and several ground-based spectrographic systems. The ejected particles were moving far too fast to be ice. Comets are usually composed of volatile ices, water, carbon dioxide, ammonia, trapped within a matrix of dust and rock. When heated by sunlight, these materials sublimate, turning from solid to gas and escaping the surface in broad plumes. The escaping gases can carry dust particles with them, forming the classic coma and tail, but this process is relatively gentle. Even during the most active outbursts, particles typically escape at speeds of a few hundred meters per second. Occasionally, high-energy fragments might approach a kilometer per second during a collapse or fragment event, but anything above that is considered extreme. The particles released by 3I Atlas didn't just break that upper boundary, they obliterated it. Data from the solar particle detectors aboard STEREO-A revealed a sharp spike in localized particle density shortly after the jet emission. But what caught analysts off guard was the Doppler signature of those particles. Calculations put their exit velocities in the range of multiple kilometers per second, a speed regime typically reserved for artificial propulsion or explosive impacts, not natural outgassing. This velocity data was soon confirmed by Earth-based spectrographs tuned to measure redshift in dust emission lines. When triangulated with the angle of observation, these readings reinforced the same conclusion. The expelled material wasn't drifting, it was accelerating. That raised the question, what kind of material behaves this way? Water ice and CO2 ice sublimate under solar radiation, but even under extreme sunlight they cannot produce the force needed to launch particles at those speeds. The thermal energy simply isn't high enough, and even with internal pressure buildup, comets don't detonate with clean directional velocity. They break, they vent, they fracture, but they don't shoot. To understand the acceleration mechanism, a team at the Jet Propulsion Laboratory ran models using different energy sources. When they simulated the jet event using known cometary compositions, no model could reproduce the observed speeds, unless the material being ejected was composed of highly energetic molecules under pressure far beyond what any natural ice reservoir could sustain. One radical idea floated in internal notes was that the jets were being driven by superheated plasma or ionized compounds, not gas expanding, from warmth, but particles being charged and pushed by directed electromagnetic forces. If the internal structure of 3I Atlas was capable of storing electrical energy, or worse, generating it, then it could in theory act as a kind of directed emitter. The jets wouldn't be passive reactions, they would be mechanisms, systems, deliberate tools. That idea was reinforced when one of the jets was seen to pulse, not continuously venting, but releasing in 3 short bursts, each timed precisely 10 seconds apart. Natural outgassing doesn't do this. Nature is chaotic, thermal, decaying. But 3I Atlas acted more like a thruster than a volcano. Some tried to find comfort in the idea of crystallized materials under immense pressure, perhaps exotic ices, compressed for centuries, now suddenly venting their built-up potential. But that still didn't explain the precision of the bursts, nor the collimated directionality. There was no debris cloud, no shattered fragments, just fast-moving particles cleanly ejected, trailing outward in linear paths, then dispersing as if magnetically damped. The escape velocity of these particles wasn't random. It was specific, measurable, and, most disturbingly, repeatable. Whatever launched them had control, and in the cold vacuum of space, when something accelerates like that without breaking apart, without heating visibly, and without explanation, one conclusion begins to press in from the margins. Maybe it's not just shedding mass. Maybe it's maneuvering. On the evening of December 7th, while much of the global astronomy community was focused on radio signals, tail anomalies, and high-velocity particles, a quieter stream of data was being analysed in real time, one that would add a new and unsettling dimension to the mystery of 3I Atlas. Several Earth-based laser ranging facilities, originally designed for tracking space debris and calibrating satellite distances, had begun a parallel effort, using ultra-short laser pulses to gather structural reflections from 3i Atlas. These are not weapons or high-power lasers. Rather, they emit focused bursts of light with nanosecond precision, allowing researchers to capture echo patterns from objects as far out as the Moon, or beyond depending on reflectivity. What they got back from 3i Atlas was something no one expected: controlled backscatter. The Mauna Kea Laser Observatory was the first to detect it. At 2117 UTC, after aligning their beam with the last known position of 3i Atlas, the observatory fired a calibrated sequence of pulses using a near-infrared diode laser. Normally such pulses either return with significant diffusion, spread across random angles, or they vanish entirely if the object lacks reflective surfaces. But the pulses aimed at 3i Atlas returned clean, focused echoes. Even more surprising, those echoes came back in two layers. This layered return is critical. The first return behaved like a typical surface reflection, faint, wide, and slightly diffused, what you'd expect from dusty regolith or icy crust. But the second echo was delayed by a precise margin, consistent across three separate bursts, and had a sharper, more coherent profile, as if bouncing from a smooth, possibly concave interior surface. When this data was sent to the European Space Operations Centre in Darmstadt, it was confirmed using a separate laser system in the Canary Islands. The scientists noticed something even more anomalous. The second echo was modulating, not just pulsing randomly, but changing slightly in amplitude every few milliseconds, too slow for turbulence, too regular for atmospheric interference. In laser ranging, this kind of modulation suggests interference within the object itself, as if the beam had entered a cavity, bounced within structured geometry, and emerged with altered phase characteristics. The word resonant appeared in multiple data logs, and for a natural object to exhibit resonance at that scale, the internal layout would have to be symmetrical, orderly, and uniform. Then came the strangest moment. The South African Astronomical Observatory attempted to replicate the readings using a longer wavelength green laser. Their team sent a sustained 1.3-second beam at the object, measuring ambient scatter as well as direct returns. Midway through the sweep, the object responded, not by reflecting, but by returning a faint pulse of its own, timed half a second after the beam ended. Initially dismissed as coincidence or instrument feedback, the response repeated 3 separate times, each following a sweep by exactly the same delay. It wasn't strong, and it didn't appear to contain encoded information. But it was real. A subtle flash, just above background noise, captured by multiple photodetectors. A response that shouldn't have been there. Was it reflection? Perhaps. Could it have been some form of surface ionization triggered by the laser beam? That was considered, but ruled unlikely due to the object's distance and the beam's low power. No natural comet should react to a ranging laser this way, not with rhythm and not with delay. Avi Loeb, after reviewing the data independently, remarked in an internal email that the backscatter and delayed pulse patterns reminded him of intentional beam interrogation, a technique used in Earth-orbiting satellite communication testing, where one platform pings another to confirm alignment or structural response. It wasn't just that the object reflected light, it behaved as if it had surfaces designed to understand what hit them. And in the vacuum of space, that kind of awareness, no matter how subtle, is the dividing line between passive matter and something else entirely. By the morning of December 7th, most observatories around the world had at least one eye locked onto 3i Atlas. The flaring jets, the strange tail behaviour, and the mounting electromagnetic oddities had already shifted it from a passive, observation target to a global focal point of inquiry. But it was the return of a very specific pattern, a sequence many had hoped was an anomaly from weeks earlier, that reignited the whispers. The pulse envelopes had come back. First reported in mid-November by low-frequency radio arrays across Australia and South Africa, the so-called pulse envelopes were not traditional signals. They didn't behave like communication bursts or flare events. Instead, they manifested as structured, ultra-low-frequency modulations buried within the background hum of space, waves of rising and falling intensity, spaced with unnerving regularity. Back then, the signal had lasted just 3 minutes, and was widely dismissed as interference. But on December 7th, within hours of the object's jets firing, the pulse envelopes returned, this time recorded by no fewer than 6 independent systems, ranging from China's Mingantu array to NASA's Deep Space Network nodes in Madrid and Goldstone. Each recorded the same thing, a rhythmic envelope wave riding a carrier frequency so low it bordered the edge of measurable space noise. The intervals were precise: 3.5 seconds of rise, a 1-second flatline followed by a 3.5-second decay, then silence, then again, repeating like a slow heartbeat. Not a tone, not a burst, but a breath. Radio astronomers knew instantly what this meant. This wasn't a flare, and it wasn't from the sun. It was coming from the object itself. The signal was directionally constrained, meaning it wasn't omnidirectional radiation, but emerged from a fixed vector originating at 3I Atlas's last known coordinates. Even more compelling, the waveform showed polarization drift over time, slowly rotating in a pattern consistent with axial spin. It was as if the pulse was attached to a rotating source, an emitter locked into the body of the object, sweeping across the sky as it turned. At first, theories centered on natural resonances. Perhaps the object's internal structure, especially if hollow, was amplifying solar wind interactions and creating standing waves. But those types of signatures don't repeat at timed intervals. They certainly don't hold perfect symmetry over hours. And the return of these pulses directly after the jet emissions raised a critical question. Was this a byproduct, or was it a broadcast? Some in the scientific community tried to play it safe, labeling the event as coherent scattering caused by localized magnetic alignment. But behind closed doors, groups were forming that entertained another possibility. The pulses were intentional. Not necessarily a language or message, but a kind of check-in, like a machine pinging its environment. If true, the implications were staggering. Adding to the mystery was the way the signal interacted with Earth's own magnetic field. Magnetometer arrays in Alaska and northern Canada picked up microfluctuations timed exactly with each pulse's decay cycle. The alterations were tiny, only detectable through deep stacking of data, but they aligned too perfectly to be random. Earth was feeling the envelope faintly through its shield. One fringe hypothesis suggested the pulses were not electromagnetic alone, but possibly coupled with scalar field emissions or exotic charge displacement. While speculative, it would explain how a signal could subtly disturb Earth's magnetic bubble from such a distance. By midday, the pulse envelopes had stopped. Just as before, they left no permanent trace, only deep questions. But this time, no one was dismissing them. In fact, several observatories reconfigured their sensors specifically to listen for the next return. Because if an object in deep space sends a pulse once, it can be noise. If it sends it again, timed, structured, and in lockstep with other events, then it may be a pattern. And in science, patterns demand explanation, even if the only one that fits is that something out there wants to be noticed. As the pulse envelopes echoed faintly across the sky, and the final burst from 3I Atlas's jets faded into cold darkness, something unexpected happened, not in space, but here on Earth. A quiet chain of internal flags began triggering inside the world's most classified systems. Seismometers began cross-referencing with magnetometers. Satellite arrays adjusted their positioning. Orbital radar grids shifted into higher sensitivity mode, not because of any one catastrophic event, but because of something far subtler: correlation. The United States Space Force's Space-Based Infrared System, SPARES, typically reserved for detecting missile launches and upper atmosphere detonations, flagged a pattern inconsistency, what it referred to as thermal event irregularity outside of standard atmospheric grid. This meant that something, cold but mechanically active, had created a spike in orbital heat mapping. Normally such readings would be ignored, but the location flagged was aligned with 3I Atlas's trajectory. That single data point was enough to escalate the signal through the Early Orbital Incident Assessment (EARSOM) framework. Within hours, similar pings began to surface from the EU Space Surveillance and Tracking (EUSST) network, as well as Japan's Quasi-Zenith satellite system. While none of these agencies publicly acknowledged a formal alert, internal logs began registering phrases like classified object gridlock override and unscheduled anomaly trajectory reconciliation. These phrases are bureaucratic, but they mean one thing: realignment for active threat monitoring. Meanwhile, underground. Beneath Cheyenne Mountain, Colorado, NORAD's space monitoring systems picked up fluctuations in Earth's ionosphere that coincided precisely with the arrival of the envelope pulses. While minor in scale, the patterns spooked system analysts, not because of size, but because of timing. The delays between pulses and atmospheric effects were too exact. A half-second here, a millisecond drift there. Across 6 cycles, the delay tightened, as if something out there was learning the rhythm of Earth's magnetic field. At the European Space Operations Center in Darmstadt, Germany, personnel noticed something even more concerning: an artificial echo in the radar return signal from a geostationary calibration satellite. That satellite, positioned far from 3i Atlas's projected path, should have had no interaction whatsoever, yet the echo had an extra signature, a ghost return, a second reflection, that didn't originate from the satellite. Analysts attempted to triangulate the reflection's origin. All coordinates pointed back to one line, the same outbound trajectory from the object. That was enough to move the system into reactive posture. Reactive posture isn't as dramatic as launch sequences or intercept protocols. It means every early warning system on Earth subtly shifts focus, tightens parameters, and prepares for decision-making without being told to panic. Satellites begin passive logging on secondary channels. Ground sensors initiate deep listening sweeps. Communication satellites cross-scan their own noise levels for foreign modulations. It's a silent orchestration of preparation, not confrontation. One of the most telling signs came from Australia's Pine Gap facility, a joint US-Australian intelligence base known for deep space surveillance. For the first time in over a year, its VLF antenna array was activated for continuous scanning. VLF, very low frequency, isn't typically used for space events. It's a mode of last resort, a way to listen for things that don't speak in conventional wavelengths. And someone, somewhere, decided it was time to listen differently. The public, of course, heard none of this. No emergency briefings, no press releases, no NASA live streams. But those inside the inner workings of planetary defense knew what these silent movements meant. Earth's early warning systems aren't just watching for nuclear launches anymore. They've started watching the skies for intention. And when a cold, distant object can alter magnetospheres, reflect directed lasers, and echo a pulse that mimics Earth's heartbeat, then even the most skeptical system must admit something's changed. Because this wasn't a flare, it wasn't a fragmenting comet, it was a presence. And the systems built to protect us just woke up to that fact. While Earth's early warning systems moved into silent observation mode, a burst of confirmation came not from the ground, but from deep space. Stereo A, the Solar Terrestrial Relations Observatory, a HED spacecraft drifting in solar orbit millions of miles from Earth, was the first to capture what would later be described in mission logs as a coherent plasma shell event originating near 3i Atlas. It started with a small elevation in the local particle flux environment. At first glance, this uptick resembled the kind of solar particle storm Stereo A is designed to study. Erratic, solar-generated gusts that occasionally flare from the sun's surface. But as the data streamed in, the pattern began to break expectations. This wasn't solar in origin, it had structure, it had form. The event unfolded over the course of 2 hours, beginning just minutes after the final observed jet burst from 3i Atlas. Instruments on Stereo A's plastic sensor array, plasma and suprathermal ion composition, began detecting a spherical front of charged particles moving not from the sun, but from a point near the object's recorded position. It wasn't random, it wasn't explosive, it was an expanding envelope, a clean radial push of ionized plasma with symmetrical density falloff, centered far from any solar mass. The implication was staggering. Something at or around 3i Atlas had released a plasma shell into the interplanetary medium. That shell travelled outward in a controlled, uniform pattern, matching the behaviour of artificial energy dispersal, rather than chaotic natural events. Plasma shells aren't unheard of. They're studied in solar flares and even certain rare magnetospheric reconnections near Earth. But they don't form in space without a large body driving the event. No natural comet, asteroid, or interstellar fragment has ever been recorded generating one. For such a structure to form in deep space without a magnetic anchor point implies one thing: intentional emission. Even more revealing was the behaviour of the shell's front. Rather than dispersing chaotically, the shell remained cohesive for nearly 12 minutes, far longer than any coronal mass ejection of comparable size. During that time, Stereo A's onboard heliospheric imager recorded faint electromagnetic shadows within the shell, striations that moved in sync as if carried by aligned internal fields. This suggested a plasma structure with internal order. One possibility, floated cautiously in internal analysis logs, was that the object had deployed a defensive screen, a kind of energetic field designed to cloak or mask emissions from deeper within. While this may sound speculative, the science behind plasma cloaking isn't new. Laboratory models have demonstrated that directed plasma waves can distort radio frequencies and block radar return. If an object of unknown origin wanted to shift or maneuver undetected, launching a shell would offer a brief moment of anonymity and motion. Compounding the intrigue, Stereo A's Secchi instrument registered a void at the shell's centre, a brief low-density region that passed over the satellite as the shell moved outward. It was as if the event had a hollow core, a spherical field with nothing at the heart of it. That's not what you see with explosive ejections, it's what you see with calculated dispersion, a shaped field launched from a source point that is no longer there. NASA teams reviewing the data at Goddard Space Flight Center stayed quiet publicly, but internal notes hinted at deep concern. The wording was precise. Shell event lacks solar anchoring. Orientation is outbound. Suggests non-stellar source. When asked for comment days later, most mission scientists deferred. One, who remained anonymous, simply said, "We're not just watching a rock anymore," because a plasma shell launched with symmetry and purpose isn't a comet's death rattle, it's a maneuver. And somewhere between those cold jets and that silent burst, 3i Atlas had done something Earth wasn't ready for. It masked its position. As global observatories traced the fallout from 3i Atlas's plasma shell, a quieter, more unsettling pattern emerged, one buried not in the chaos of particles or electromagnetic pulses, but in the rhythm of timing. It came not from what the object did, but when it did it. A team at the Indian Institute of Astrophysics, working on a separate time synchronization project, noticed something strange in the log files. The jet emissions from 3i Atlas had occurred exactly at the moment Earth's terminator line passed over specific radio observatories. The terminator line is the boundary between night and day on Earth, a moving threshold that constantly travels across the planet due to its rotation. At any given moment, this line divides Earth into a sunlit side and a shadowed side. For astronomers, it represents a critical shift in observational clarity. When the sky transitions from brightness to darkness, ground-based sensors adjust, recalibrate, or even temporarily shut down to manage light interference. But what if something, or someone, was aware of that cycle? The emissions from 3i Atlas's jets weren't random bursts. They were time-locked events. Each major jet ignition, across a period of 5 Earth rotations, occurred within a narrow 90-second window as the terminator line passed over a key monitoring point. Mauna Kea, Alma in Chile, Pine Gap in Australia, and the Deep Space Network dish in Madrid. Different hemispheres, different latitudes, but always within that same twilight corridor. Initially, this was dismissed as coincidence. Earth rotates every 24 hours after all. But when researchers overlaid the ignition timings onto a moving global terminator simulation, a haunting symmetry appeared. The first jet fired just as Hawaii's sensors entered shadow. The second when Australia's tracking moved into daylight. The third mirrored the moment the Madrid facility switched from thermal to optical imaging mode, and so on. The implication was jarring. The object wasn't just acting, it was synchronizing. Some researchers argued this could be due to solar influence. Perhaps the object's surface chemistry responded to radiation angles that just happened to align with Earth's day-night shifts. But that theory collapsed when Stereo A's remote imaging confirmed that solar angle changes at 3 Atlas's position were minimal, nowhere near enough to trigger surface activity on their own. Another layer was uncovered when teams began analyzing Earth's outbound telemetry patterns. During transitions at the terminator line, ground-based systems often shift communication bands. For a few minutes, encrypted telemetry drops or repositions, brief windows when data goes quiet. Those windows matched the jet emissions almost perfectly. This left one terrifying possibility. 3i Atlas wasn't reacting to light, it was reacting to blindness. Whenever Earth's sensors dipped in awareness, whether from sunlight interference or recalibration downtimes, the object moved, like a submarine waiting for sonar to reset, like a thief slipping through motion detectors during a scheduled reset. And if it could predict those windows, that meant it had awareness, not just of Earth's orbit or solar behaviour, but of our detection systems. More concerning still, the last jet emission on record didn't occur near a terminator line. It came half a rotation early, during a moment of unusually high auroral activity near Earth's poles, a moment when magnetometers were disrupted and tracking was skewed. In other words, another blind spot. This final ignition wasn't just timed, it was calculated. And so, a new narrative began forming among those in the know. Maybe the jets aren't propulsion, maybe they aren't outgassing, maybe they're manoeuvres, but only when we look away, only when we're blind for just long enough. Because when the rhythm of an interstellar object mirrors the rotation of Earth, not by accident, but by strategy, it's not just an object anymore, it's a player. And Earth has just realised it's not alone in watching the clock. Just when the world's space agencies began adjusting to the idea that 3i Atlas was more than a passive comet, the skies delivered something no one was prepared for. A flicker, not a flare, not a burst, but a fleeting appearance of something else. It came from the Canada-France-Hawaii telescope, CFHT, perched atop Mauna Kea during a routine tracking pass on December the 7th. The primary focus was 3i Atlas, which had just finished its sequence of jet emissions and appeared, on the surface, to have stabilised. But in the far corner of the wide-field infrared sensor array, technicians noticed something odd. A transient light source, near the tail, that shouldn't have been there. It lasted less than 6 seconds. At first glance, it was written off as cosmic ray interference, or maybe even a sensor ghost, something astronomers are trained to ignore. But an automated alert was triggered anyway, because the flicker had motion. It appeared, brightened quickly, and then began to arc slightly before fading, a curve barely perceptible, but real. The event might have gone unnoticed if not for the synchronized efforts of the Vera C. Rubin Observatory in Chile, which captured a similar anomaly just 3 minutes later. Same area of space, same angular drift. And when data from both facilities was synchronized, it revealed something stunning. Parallax. The tiny angular shift between the two observatories' perspectives confirmed it wasn't a lens artifact. It was a real object, but it wasn't stable. Unlike 3i Atlas, which had a predictable path and consistent spectral data, this second signature was erratic. Its brightness curve suggested a rotating body, or more precisely a reflective surface that caught light briefly before falling back into shadow. The flicker wasn't emission, it was reflection. That detail made all the difference, because it meant whatever flickered into view wasn't hot, wasn't combusting, and wasn't outgassing like a natural body. It was cold, inert, and most disturbingly, geometrically smooth. The surface return showed a flat spectral profile consistent with reflective metal or composite material, something rarely seen in deep space unless you're looking at space debris or artificial satellites, except there's no debris at interstellar speeds. This left analysts scrambling. If this was a fragment of 3i Atlas, why hadn't it been seen before? Why wasn't it tumbling like every known shattered object in motion? And why had it revealed itself only once, under a perfect angle? One theory took hold among the more daring scientists. This was a companion, a secondary object, possibly tethered or operating in loose formation with 3i Atlas, but cloaked by reflectivity, positioning, or even intentional design. It might only be visible under very specific solar angles, just enough for the sun's light to bounce toward Earth, like a mirror catching a glint across a dark room. Another chilling possibility was floated. The object was repositioning. The flicker's curved motion and its sudden disappearance suggested not orbital drift but active course correction. That's not how rocks move, it's how craft move. And then came the silence. No further flickers, no follow-up reflections. Telescopes were repositioned, filters adjusted, sensors recalibrated, but it was gone. which raised the biggest question of all. Did it want to be seen? Because in space, a 6-second visibility window is deliberate. It's a signal, a test, a whisper. The silence that followed wasn't empty, it was strategic. As if whatever was accompanying 3i Atlas had opened a door for a single breath, peeked into our world, and then closed it again. Now, 2 possibilities remain. Either Earth caught a glimpse of a lost fragment in perfect sunlight, or we were just blinked at. And in both cases, what's more terrifying isn't what we saw, it's what we didn't.